From C, AB to I for any F in C, AB by whenever it acts on F, it gives us supremum over X in AB of absolute value of F of X. If we define this, then defer on C, AB together with that functional is a non-linear space. Please, we have to be very, very careful here. This is a non-linear space, meaning that the functional defined by this is a norm on what? On CAB.
Yes.
So we need to check that the four properties defining a norm are satisfied. But before that, what is the idea behind the definition of this? And by the way, what I mean is that definition, is it really well defined? This functional, is it well defined? What will guide us is, that's why I'm saying, and I continue saying this, that elementary analysis is very important course. And whoever wants to go further, to do a kind of meaningful work in mathematics, especially at this level, should have real analysis at the tip of his or her fingers. Without that, you will not go far. Actually, what is happening us here is the following. The absolute value function is a continuous function, we know. F by where it's coming from is a continuous function of AB on the interval what? AB. I don't know if you get my point. So what you are seeing here, what is playing out here is a kind of composition of two continuous functions. The absolute value function composed by what? By F. That is what is playing out here. On what interval? On the interval AB. And the composition of two continuous functions is what? Continuous. I hope you're following me. So both of them are continuous. On what? On the closed bounded interval. This refers you back to a knowledge that will be gotten from the elementary mathematical analysis. That a continuous function, a continuous real-valued function, on the closed and bounded interval AB is bounded.
Yes.
Is bounded. And for the fact that it's bounded, this supremum exists. And this supremum exists, you can now, and is a real number. Therefore, we can define this to be that supremum. And there are other things you should know about continuous functions on the closed and bounded interval. It's a very important, that particular, this what I'm talking about now is a very important notion that must be properly understood, because that is actually the fundamental, where the fundamental theory of optimization emanated from. A continuous function on the closed and bounded interval has a minimum, has what? A maximum. There are other interesting things you should know about this. Do you know that the continuous function in the closed and bounded interval is uniformly continuous?
Uniform.
You understand? Just continuity on the closed and bounded interval guarantees uniform continuity on that closed and bounded interval. Remember, not every continuous function is uniformly continuous.
Yes.
But every uniformly continuous function is what? Continuous. But this time around, just that because of the domain, a continuous function on this is what? Uniformly continuous.
What is projected to compactness? What is projected in compactness?
Look at this now. R is a finite dimensional space.
Yeah.
Closed bounded
Interval.
interval on R in R
It's
is
com-
what? It's
it's
compact.
compact.
By what? You can say by Hembury theorem.
Hembury theorem, yeah.
I don't know if you know what I'm talking about.
Yes.
It's compact. Good. Now, this particular thing you've already seen in R you can now look for its replica
Yes.
on Rn.
Okay.
Rn is a finite dimensional space. A compact set in a finite dimensional space is characterized by what? Being closed and what?
Bounded.
Bounded. There's a subset of a finite dimensional space is compact if finite is closed what and bounded by Hembury theorem. Therefore, when you now take a function f from call that compact set K to R continuous, once you put continuity, then that f is bounded. And not only that it's bounded, it has a minimum in K. That there's a point in K where the minimum is attained. There's a point in K where the maximum is attained. And it happened that this K, if you're doing optimization problem of the form, minimize it or maximize, minimize f of x such that this is what we say subject
Yes.
to.
Okay.
What do you have? The constraint. What is the constraint? X is in K. Reduce is a minimization problem.
Okay.
So what guarantees that the minimum exists? The
Okay.
minimum exists is that f is a continuous function and a compact set. No close and bounded set. Tells you that this is what at times those in optimization theory, for instance, do not look at because they take it for granted. They will just start a minimization problem with their, but under normal condition, you first of all check that the problem you're looking at is well defined and what you're looking for is in existence before you start looking for it. It's just like, for instance, you have a pool of dirty pond and somebody tells you to go there and get a coin. That's it. You must first of all establish the existence of a coin in the pond before you start looking for it. So if it's not guaranteed that it exists, then what's the need? And that is why, for instance, if you see these people that are working in oil company, before they talk about drilling, they will first of all do a kind of survey and other things before they for the existence before.
There should be traces of some rocks,
something that before they start whatever they want to do. So if you don't know that there is existence, that's why, for instance, existence theory in whatever we are doing is very important.
It's very important. You could be building structures in
without foundation.
without foundation.
So you must establish existence before. And that is why most of the things we do, for instance, at this age of iterative, you assume the existence of solution before you start talking about getting the solution. Oh, it's clear. So let us try to see. The well-definedness of this now is clear, I hope.
Yes.
This is a continuous function. The composition is a continuous function on the closed and bounded interval, and therefore the supreme word exists. So that tells us that the general definition is okay. That's the function. This is well defined. The next thing is to check that all those properties are what? Satisfied. B, A, B, O, R, given for all F in C, A, B, by equals supreme over X in AB of absolute value of f of x, we show that this is a norm given by is a norm on what? On C AB. We show that it's a norm on C AB. As follows. For FG in C AB and then lambda in R, observe that I, watch here, this is obvious. Observe that I, for any x we pick in AB, for any x I pick in AB, 0 is less than or equal to absolute value of f of x.
Okay.
And then absolute value of f of x is less than or equal to supremum over x in AB of absolute value of f of x. In AB, this is always true because of the property of absolute value, and also this is true because of the property of what? Supremum. Therefore, what we have? Therefore, 0 is less than or equal to supremum. Since this is true for all x in AB, and this is true for all x in AB, remember for all x in AB because of this. This is a number.
Yes.
So it's no longer dependent on x. So for the fact that this is less or equal to this, and this one is less or equal to this one, means therefore that 0 is less or, is it not?
Yes.
0 is less than or equal to sup x in what? In AB of what? Absolute value of f of x, which by our definition is what we call this function. That's it. So what we have is that what? For any f in what? In C, A what? AB. There's something I find difficult to do it. For any f we pick it CAB, this thing here is greater or equal to 0. I say this thing here. I am not until I verify that those 4 conditions are true, then I'll call it a norm. But for the fact that I've not verified, I'll be saying the function producing this. This is greater or equal to 0. That's what kind of number I want to go 2 ways. I want to show, what we want to show now is that this equal to 0 if and only if f is equal to what? 0. This is what I want to show. Question mark there means that we've not been able to show that. And this if and only if, I would break into 2. If and only if means double implications. That is, look, if and only if. So it's the same thing as what? This double implication. So in trying to show if and only if case, what we normally do is what? We'll try to that double implication, we tear it into 2. Separate it to. One is the one going this way, and the other one is the one going this way. Are you with me?
Yes.
So considering the one going this way, what do? You assume the first statement and prove that the conclusion is true. And the other one, you assume the second one and conclude. That's the fundamental situation. Now, remember, question mark means that this should be verified. Now, I'll go this way first. Meaning, suppose, okay, for
Yes,
When you suppose that that function, that thing is equal to what? 0. And we show that f is 0. That is to say that f is a 0 function. Be careful, please. This 0 is 0 as a real number.
Yes.
This particular 0 is a 0
As a
function. So there are two zeros laying out there. Good. Now, we show that this is the case. But this thing equal to 0, implies, let me say, implies that, actually it's equivalent but, implies that what? Supremum over x in what? In AB of what? Absolute value of f of x is equal to what? 0.
Yeah.
Partially. But for any x we pick in what? In AB, 0 is less or equal to absolute value of f of x. And what? Absolute value of f of x is less than or equal to supreme over x in what? In AB of what? Absolute value of f of x. Okay, follow me. Remember, please, to avoid confusion, if I say for any x in AB, and I write this, and I am talking about x, here we must identify that this x not necessarily this x.
Yes.
Because I can still use the fact that x here is dummy to say supreme over t in AB of absolute value of f of t.
So that one is a number.
This is a number, that's what I'm saying. Then here, what I want to make, what I'm trying to point out is where x is running. X is running here, as well as what? Here. But here, this is what? A number. Please, we have to be very careful about that. Therefore, what are we? Therefore,
soup is equal to 0.
thus, with soup over x in AB, absolute value of f of x equal to 0, we obtain that, what do we obtain? For any x we pick in AB, watch me please, 0 is less than or equal to absolute value of f of x, and this is less than or equal to supremum over x in what? In AB of absolute value of f of x, for this is equal to what? 0. This means therefore that for any x in AB, 0 is less than or equal to f of x in absolute value, less than or equal to 0. And this is what? This implies that what? Thus, for any x in AB, absolute value of f of x is equal to 0. This implies that for any x in AB, f of x is equal to 0. Plus absolute value of something equals 0. If I know that is equal to what? 0. But what does this mean? For any x in AB, f of x is equal to 0. What does that mean? Giving me any point, f takes that point to 0. Meaning that f is a 0 number. Thus, f is what? Is 0. Is 0 number. Then going back, suppose f is 0. This, I didn't want to combine the two. You have combined the two and get the result. If I'm only there, but I just decided to break it so that things will be Clear. I'm assuming no knowledge of the entire thing. No knowledge at all. So that I believe that we can work this way. Suppose f is 0. If f is 0, then for all x in what? In AB, f of x is equal to 0. This implies that for any x we pick in what? In AB, absolute value of f of x is equal to what? 0. For any x we pick, absolute value of f of x is what? Is 0. Therefore, since absolute value of f of x is 0 for all x in AB, we must have here that if we take supremum over x in AB of absolute value of f of x, we must get what? 0. Because you're taking supremum of 0. Supremum of a point is that point. So that will give us what is 0. And this implies that what? That value, which is this, is 0. So what have we got? What we got is that this is 0 if and only if f is what? Is 0. The third condition that for any f we pick in CAB and for any lambda in the norm of that if the acting on lambda f will give us good. So we check that is equal to what? Absolute value of lambda when it acts on f. This does take we go by definition. To see this, we observe that for any f in C, A, B, and for any lambda in R, by definition, this is defined as supremum over x in AB of absolute value of lambda acting on what? On x. That's what it will mean. Which by our definition still is the same thing as supremum over x in AB of absolute value of lambda f of x. Absolute value of lambda f of x. And this is nothing but supremum over x in AB of absolute value of lambda, absolute value of f of x. That's what it is. But this is a non-negative constant and independent of x. By the property of supremum, we can bring it out and retain the supremum because it's non-negative. It's not negative. If it's negative, if once you bring it out, this changes to infimum. I hope you know. Yeah. So this is the same as absolute value of lambda supremum over x in what? In AB of what? Of absolute value of f of x. But this is nothing but that evaluation. Or that value. So this is nothing but absolute value of lambda on this value. So we have that. So what we have is therefore that for any f in CAB, for any lambda in R, this is equal to absolute value of lambda when it acts on f. So that's it. Then the last one is the triangle inequality. We want to check that for any FG we pick, you know. I started with that so that you know where we're picking. We've already said assuming F and G are what are given. So we want to check that this plus G will be less than or equal to when it acts on F plus what when it acts on what on G. This is another thing to verify. So how do we go about this? The same thing. We also observe that I want us to observe that for any FG in what? In C, AB. Please when I write C, AB, I can even use this notation is even better than what I've been using. What I'm using is putting this in bracket. That's the normal thing. Yeah? For any FG in C, AB, we shall look at a base as equal to what? Supremum over XC in what? In AB of absolute value of F plus G acting on X first. This is what it is by definition. And which if we go further by a definition of sum, we can now write it as what? Supremum over X in what? In AB over X in AB of what? Absolute value of F of X. But we know that for any X in AB, for any X we pick in AB, absolute value of F of X plus G of X is less than or equal to absolute value of F of X plus what? Absolute value of G of X. We know this.
Yes.
That's the triangle inequality of absolute value. You're following me? For any X we pick in AB, this particular absolute value is less than or equal to this plus this. Do we agree?
Yeah.
Huh? Are you with me?
Yes.
That's the
Is it
triangle inequality we know.
Yes.
Good. And then absolute value of F of X plus absolute value of G of X is less than or equal to supremum over X in AB of absolute value of F of X plus supremum over X in AB of what? Absolute value of what? G of X. This is coming from the fact that this one is less or equal to this one, and this one is less or equal to that one.
Their sum also.
Okay.
Therefore, their sum will be less than or equal to this sum. Hope it's clear.
Yes. Yes.
Yes. It's clear, but I'm trying to figure it in my head.
So look at this. If A is less or equal to
B.
alpha
Okay.
and B is less or equal to beta, then A plus B will be less or equal to alpha plus beta.
Yeah.
Adding the two inequalities.
But I agree with you. I was just using numbers in my head to check it.
To check it. Have you seen it? If you've gotten it, then that's fine. So, having gotten that for any X in there, this happens. And from the property of supremum, this one happens. It means that this is less or equal to this, and this is less or equal to that one. So what I have is therefore, for any X in what? In AB. Are you with me?
Yes.
Absolute value
Of
of F of X plus 1 G of X is less than or equal to what? Supremum over X in what? In AB of absolute value of F of X plus supremum over X in what? In AB of what? Absolute value of G of X. This means therefore that this number here is an upper bound
Upper bound.
for this collection.
Okay.
As is an upper bound, the least upper bound of this collection must be smaller than what it is. Are you with me? I hope you're following me.
Yes, well.
Therefore, supremum over x in AB of what? Absolute value of f of x plus g of x must be less than or equal to supremum over x in AB of absolute value of f of x plus what? Supremum over x in what? In AB of absolute value of g of x. This is where we are. But what is this supremum? From our what we just identified. This is nothing but this, which is exactly this. And then what does that mean? This means therefore that this plus g is less than or equal to this one is what? That on f plus what? That on g. And that completes the proof. So that means therefore, this functional on from CAB to R given for all f in what C A B by when it acts on f, it produces supremum over x in AB of absolute value of f of x is a norm on what? On C A B. The norm on C A B. So that the pair C A B together with that is what? Is a norm space. It's somehow, I don't know how to describe it, using supremum. That is the defining this to be the supremum. Why am I saying this? So using supremum is too big. What I'm trying to say is that what, rather than supremum, we use maximum over what? X in what? AB of absolute value, because the maximum of what exists by that theory we talked about. This is a continuous function on closed interval AB, and therefore what? The maximum exists. So if I replace the supremum with by maximum, it will still work. Are you with me? It still work. But look, where will it be necessary to make the restrict ourselves to the supremum? If I'm talking about, for instance, C A B, that's the only point interval AB, or any other thing, or you remove A and you get what I'm talking about. In that particular case, I can talk about the supremum, because we are not sure
that it
whether the supremum is what, whether the maximum is attained here. You understand? But I know that the supremum exists.
So even if it's from A, even if it's a ray from A to plus infinity.
Infinity. From A to plus infinity, once from A to plus infinity, we have to be very, very careful. Because from A to plus infinity, you do not know whether the supremum exists. But for the open bounded interval, I think we can check that the supremum exists, but not necessarily the maximum.